أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. uh, in the course of thermodynamics, having the course code of PHY331, we will discuss something about the generalized work and composite systems. We need to understand the concept of generalized work, as we have developed the work for different configuration for different system, 1-dimensional, 2-dimensional and 3-dimensional, and develop the equation of state for each of that particular system. So we need to generalize the idea. If we have general variables, how many equation of state we need and how many thermodynamic coordinate we need. So we need to generalize the idea in the end of this chapter. So this lecture is almost the end of this chapter. We also need to develop the concept of composite systems. If there are more than 3 variables, normally the system was described by 3 variables, that was the PVT, the pressure, volume and temperature. So if we have more than 3 variables, so what we will do in that case? In the case of 3 variable, we have 2 variable as an independent coordinate and 1 variable as a dependent coordinate. So if we have more than 3 systems, more than 3 thermodynamic variable system, how we can deal with such systems, and how many equation of state will be needed for that particular system. So that is called as a composite system. That is also a part of our lecture, or today lecture. First we need to know about generalized work. Actually, the work is a product of intensive and extensive coordinate. We discussed the nature of intensive and extensive coordinate in the last few lectures. Actually, intensive and extensive coordinates are relevant to the configuration of a systems. So when we draw the intensive coordinate against the corresponding extensive coordinate, then the work diagram is developed. And we developed the work diagram for each particular system in the previous cases. So each of that particular system has a separate work diagram. So work diagram may be introduced that does not refer to a particular systems, and it will be actually the general work diagram. So we are actually interested to develop a generalized work diagram. It will not be concerned with any particular system like we had done. If you remember, in previous lecture we had calculated the work done for changing the length of a wire, for changing the surface of that any particular film, and maybe the work done in electrochemical cells. And just in previous class we discussed the work done in changing the polarization of a dielectric material. Similarly, that has a separate equation. It's a separate equation of state. Separate thermodynamic coordinate were used and separate equation of state were developed for that. And even after that we discussed and we calculated the work done in changing the total magnetization of a paramagnetic solids. So it means in all the cases we followed a proper channel, and in that channel we develop a separate we develop the separate thermodynamic variable for that, and at the end we develop a separate and simple equation of state for that. So today lecture we are basically interested how we can develop a generalized equation of state or generalized variables which can be used for many systems, not for a single systems. So we need to we have some intensive and extensive variables. When the extensive coordinates are like the pressure, ta, rho and epsilon, e, and similarly mu naught h are referred as the generalized forces. These are the generalized forces, and these are actually the and some extensive coordinates such like v, l, a, z, p and m, that are actually generalized displacement. If we see in the work equation we have two things, one is the force and other is the displacement. So in all particular cases we have separate forces and separate displacement. So if we generalize it, we will have generalized force, and in the same way we will have generalized displacement. So the multiplication of generalized force and generalized displacement will lead to a generalized work. So similarly, the intensive coordinates are the intensive quantity, that is the pressure, tau, rho, and epsilon and E, and similarly mu naught H, that are actually the force. The mu naught H is mu naught is multiplied by H to give to represent it as a force, a dimension of force. So similarly, we have displacement for that, and that displacement is expressed in V, L, A, Z, rho, and M, that are actually the generalized displacement that particular cases. So the work done can be represented through a generalized work diagram, where the generalized force X is drawn against a generalized displacement, that is Y. So in that case, due to the unit system, the magnetic field H must be multiplied by mu naught to produce a force-like quantity, because the other has a force-like quantity, but this H has not a force-like quantity, so therefore we need to multiply by mu naught H. So a simple summary of this slide is that the product of generalized force and generalized displacement gives us generalized work, and we are mainly interested in this lecture about the generalized work. So we need to generalize the idea, develop a work so that it can be used for many particular systems. So we have different systems where we can discuss the generalized work and generalized coordinates, that is actually the intensive and extensive coordinates. So again, we have two things. One is the generalized force, and other is generalized displacement. So if you consider the hydrostatic system, so the pressure that is measured in Pascal, that is the generalized force. Similarly, the volume that is measured in cubic meter, that is the generalized displacement, and the magnitude of work done is equal to minus p dv. If you consider changing the length of a wire, so the tension tau, that is a generalized force, and it is measured in Newton. So the generalized displacement in this case is a length that is measured in meters. So what will be the magnitude of generalized work in this case? That will be tau dl. Similarly, if you consider surface film, so in this case rho, surface tension, that is expressed in the unit of Newton per meter, and similarly the area that is expressed in cubic meters, in square meters, that is actually the generalized displacement. So the product of generalized force and generalized displacement which gives us the generalized work, and it is equal to gamma dA. So similarly, if we consider electrochemical cell, in case of electrochemical cell we have epsilon, that actually gives us the electromotive force, capital. So that electromotive force is measured in the unit of volt, and similarly charge that is stored on the plates of the capacitor, that is measured in the unit of coulomb C. So that are the generalized force and generalized displacement respectively, and its product that is equal to epsilon dz, that is the generalized work. For the case of dielectric solid, we have electric field that is measured in unit of volt per meter, that is actually generalized force, and we have generalized displacement that is actually rho, that is measured in coulomb meter. So the product of generalized force and generalized displacement gives us generalized work, and it is equal to E d rho. And at the end we have a paramagnetic solid, that was the the previous lecture. We have mu naught H, that is measured in Newton per ampere meter, and the magnetization is ampere meter square meters, and is mu naught H dm, that is actually the generalized work. So in all cases we have summarized from this table, that the product of the generalized force and generalized displacement gives us generalized work. So the next part of the lecture is devoted to the understanding of composite systems. We have different composite systems. In the whole chapter we discuss simple system, and the equilibrium configuration of that systems are described by three coordinates. The three coordinate were PVT, that was actually the pressure, volume and temperatures, and among the three coordinates, two were independent and one was the dependent coordinate, and in all particular systems among the three coordinate, one was the temperature coordinate. So PVTH, again the temperature was common in all the systems. So what happens, we need to consider a system that has more than three coordinate and more than one equation of state. So in a simple system, when the system was described by three coordinate, the equilibrium configuration was described by a single equation of states. So if we have more variables, I mean more than three variables, more than three coordinates, what happen, we may have more than one equation of states. So in this case we consider a simple system that has more than three coordinates. So similarly, to describe this particular system, we will need more than one equation of states. In this case we have two particular systems. Here this is one system and this is another system, and these systems are connected with each other by diathermic wall. It means that the temperature is same on the both sides of the boundary. So it means the diathermic wall can easily allow the temperature to exchange in between the two systems. The pressure and volume of this particular system are represented by P and V, and similarly pressure and volume of the second system are represented by P dash and V dash. So this system as a whole is connected with the heat reservoir. So we need to explain these systems and describe this system, this composite system, in terms of five thermodynamic coordinates that are actually P, V, P dash, V dash and T. That is actually the temperature. These five thermodynamic coordinates are used to express these systems. So similarly, when we deal with this system, we will need at least two equation of state to describe the equilibrium configuration of this system. This is actually the work diagram that is drawn for it. So we will discuss at the end about this work diagram. So in this case we have hydrostatic system that is separated by diathermic wall, and the thermodynamic coordinates are represented by P, V, P dash, V dash and T, and two equation of state will be needed for this. So work done in this case will be given by, that is actually the product of force and displacement. So we have the work done for both the system. For the first system, that is equal to minus P dV, and for the second system is minus P dash dV dash. So we need to explain the work diagram for that. How we can develop the work diagram for this particular system? We need to draw the work diagram on a rectangular axis, and the coordinate in this case are V, V dash and T. V is the volume of the first system, V dash is the volume of the second system, and T is the temperature of both the system, because both have the same temperature. So what happened? The isothermal process is the curve is actually with a constant temperature. If you consider here this curve, that has the constant temperature, because the temperature is not varying in this curve. So similarly, if you consider the volume constant, so this curve is represented, this face is represented by volume is equal to constant. We have line A and B. The line A and B lies on the vertical line. AB lies on the vertical line. So in this case no work is done because the volume is constant. So therefore the line AB represents a process in which no work is done. So this is actually this particular system. So we have some other example. This was the first example of composite system. What we had done in this case, we had actually 5 variables to describe these systems. Two pressure and volume for the first system, 2 pressure and volume for the second system represented by P dash V dash, and similarly one is the common variable, that is the temperature. So we needed 5 variables. So more than 3 variables are present in this system, so that is why the composite systems. And similarly we had the complicated work diagram in this case, because this is a 3-dimensional work diagram, but in other cases we have only two-dimensional work diagram because we have only 2 independent coordinates. So in this was the particular system and the explanation of this work diagram for that system, that how many curves we have, that is the temperature constant and volume constant curve, and the curve are the lines where no work is done, that is the AB line. So we consider some other systems. If we have some other system, how we can deal with this? And the other system is the example of a ideal paramagnetic gas at low pressures. This is the example of ideal paramagnetic gas at low pressure. Keep in mind, this is the gas, that is oxygen gas, closed in the cylinder. This piston is here, that is movable pistons, and this system is connected with a heat reservoir. A solenoid is surrounding the system. So there is a wire in the form of solenoid, so that is surrounding the system. So this is actually the constant. We are considering an ideal paramagnetic gas at low pressures. So the oxygen have pressure P and the volume V, that is varied with the piston cylinder combination, and it is immersed in a magnetic field which is changed by varying the current in the solenoid. If we change the current in this solenoid, in this wire, so what will happen? The attached magnetic field with this current will be changed, and it will change the system, because the whole system is immersed in a magnetic field, and this magnetic field can be changed by changing the current in the surrounding solenoid. So the temperature of the gas is considered to be constant here. So how many coordinates we need to express? We describe these systems. Again, we have more than 3 coordinates, thermodynamic coordinate needed to describe this system, and that is why we will have more than one equation of state to describe the equilibrium configuration of these systems. Normally we need 2 equation of state to describe these systems. Among these 5 coordinates, that is pressure, volume, mu naught, h, m, and t, 3 are independent coordinate while 2 are dependent coordinates. So for expressing this system, we need to have 2 equation of state for this to develop or to describe the equilibrium configuration of this system. The first one is the PV is equal to nRT, that is the ideal gas equation. This is the equation of state for this particular system. And the second one is the Curie law, that is also described that could be expressed by m is equal to C is the subscript h divided by t. That has that is also a second equation of state for this particular systems. So when we discuss the work done in this case, this is the Curie law. So the infinitesimal work done is given by, in this case the infinitesimal work is given by dW is equal to minus P dV plus mu naught h dm. So this is actually the equation of work done. dW is equal to minus P dV plus mu naught h dm. So the independent coordinate in this case are T, V, and M, and the coordinates that are plotted to draw a work diagram for this particular case is like this. So the vertical axis represent a process in which no work is done. So we have 5 coordinates in this case. So in this case the coordinate are drawn rectangularly with each other, and it is like V, T, and M. M is the magnetization, V is the volume, and T is the temperature. We have different curves for that. We have a constant temperature curves, that is the up, that is in the vertical axis, and similarly we have a constant volume curve, and we have also a line, the same line like we had for the previous systems, that in which no work is done. So we have generally the work done, that is equal to minus P dV plus mu naught h dm. So this is general for this particular system about the paramagnetic solids. If we more generalize the same thing and we express this in terms of more general variables, that will be like y x, y dash, x dash, and the work done in this case will be equal to dW is equal to y dx plus y dash dx dash. So this is actually the work done when we express the variable in terms of this. And again, temperature is common in all of them, so we have temperature as a common coordinate, so 5 coordinates are needed for that. So this is equal to dw is equal to y dx plus y dash dx dash. So the most convenient coordinate for this system are tx and x dash. So this is something about the composite systems and generalized composite system. And in this case we have developed how we can generalize the work done for this different system. This is almost the end of this chapter, so I hope we can start a new lecture and a new chapter in the next lecture, inshallah. Thank you very much.